3.2, we have exponential and logistic modeling. 3.2, exponential and logistic modeling. All right, so, okay, so let's talk about exponential modeling first. So we're talking about exponential modeling. Okay, exponential modeling is you're gonna have a y is equal to e to the x or something like that, or you can have something like b to the ax or whatever, okay? So when you talk about, let's say that we have now I put $1,000 into a bank account, which is going to make me, I don't know, 6% return every year, okay? So my money at time t is going to be the original amount. Every year, I am going to accrue 6%. And after t years, this is how much money I'm going to have, right? Because the first year, I'm going to have 1,060, right? The next year, I'm going to start with 1,060, and I'm going to multiply that by 1.06. So basically, it turns out like this, right? 1.06 plus how many years, right? So every year you're going to tack on, you're going to multiply another 1.06 to whatever you had before. Okay? All right. So this is a exponential growth because I'm getting larger, right? Okay. Sometimes things decay and you get less than that, right? So let's say that I have a $1,000 car, right? So every year it's going to depreciate, right? Every year it's going to depreciate. So every year I'm going to lose 5% of its value, right? So a $1,000 car becomes, next year it's going to be worth $950. The next year is going to be $950 times 0.95 times 0.95, right? So it's going to be 1,000 times 0.95 t. So the difference between a growth and a decay is whether or not this guy here, the base, is greater than or equal or less than 1, basically, right? Okay, all right. So let's see, go to page 265 in the middle, there's a blue box. Go ahead and then read that for me, see if that makes any sense. Okay. If it doesn't make any sense, you guys can't tell me anyway, so you guys are stuck. All right, so example number 1. Example number 1, tell whether the population model is an exponential growth function or an exponential decay function. Find the constant percentage rate of growth or decay. Okay, so I have the population of San Jose, and it's going to be population at time t is going to be equal to 759 times 1.064 to the t. And then in B, you have Detroit. Detroit starts with 1.2 million. Oh, 0.9858 T. Okay, again, so San Jose population is getting larger, right? Because it's greater than a 1. I'm multiplying by greater than 1. Okay. Detroit, the population is decreasing or decaying away because I have less than the one number here, right? Okay, and the rate that this guy is increasing is 0.64%, right? Because the rate that is increasing is that, right? Because that's what I'm adding all the time. So percent-wise, it would be that, 0.64%, right? Over here, this is 1 minus x is 0.9858. So x is going to be equal to 0.0142. So it's decaying at a 1.42% rate, okay? 0.0142, right? Okay, pretty simple stuff there. Example number 2. Example number 2. Determine the exponential function with an initial value of 12, increasing at a rate of 8% per year. So the initial value was 12, and it is growing at 8%. Pretty simple. Okay, blah, 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 blah. Okay, we're good there. Let's go to example number 3. Example number 3, we're going to talk about modeling bacterial growth. Modeling bacterial growth. And we have, suppose that the culture of 100 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be that many. So you start with 100, right? And every hour it grows by 2. And I want to find out when this is going to be this many, right? So as of now, since we haven't talked about logs and stuff like logarithmic function or whatever, you're just going to go ahead and graph this and see where it meets this, right? Pretty simple, okay? And it turns out that t is going to be equal to not that long, actually, not even 12 hours. Okay, all right. Okay, so there you go. So just going to put it in your calculator, graph it out, and see where they meet. Example number 4, now we're going to model radioactive decay. Radioactive decay. Suppose the half-life of a certain radioactive substance is 20 days, and there are 5 grams right now. Find the time that it will be 1 gram of substance remaining, okay? So I start with 5 grams. I have 5 grams. 20 days later, how much am I going to have left? I am going to have 2.5 grams, right? Because the half-life is 20 days. The time that it takes for it to decay to half of its original value is called the half-life, right? It's not just a name of a video game, right? So another 20 days, now I'm going to have 1.25, so I'm going to have half of that, right? And then another 20 days later, I'm going to have half of that, right? So somewhere it's got to be at least 40 days, but not more than 60 days, right? Okay. So the way you're going to figure it out is the same way we did last time, okay? So I'm going to, well, not the same way we did last time. So you start with what? You start with 5 grams. Start with 5 grams. Then every 20 days, so is it asking for the number of half-lives? Just find the time. Just find the time, right? Let's just find the time, right? Sometime later, it's going to be 1, right? So basically, again, you're going to go ahead and plot this, put in your calculator and graph it and see when it hits 1, right? Or you can divide by 5 on each side and go like that. And so find out when this guy becomes 0.2, okay? All right, I'm just going to graph it and see where that happens. Okay, and if you do that, it looks like it's going to be 46.44 days, which is right. We said, right? It had to be greater than 40 days, but less than 60 days, right? Okay, all right, so there you go. That's how that works. And let's do one more here. Determining altitude from atmospheric pressure. Altitude from atmospheric pressure. Okay. Example number 5. Find the altitude above sea level at which the atmospheric pressure is 4 pounds. Okay, and the equation that you're going to use here is scientists have established that atmospheric pressure at sea level is 14.7 psi, pounds per square inch, 14.7 psi, and the pressures are reduced by half for each 3.6 miles above sea level, okay? So 1/2, and as it goes up, right? So we'll just call that D, I guess. And we need to find out when it is going to be 4 pounds, right? 4 psi. So I'm going to go ahead and divide this by 14.7. I'm going to end up with that. All right, and just go ahead, and this is whatever this is going to be if I do that. They didn't do it that way. But anyway, so you go ahead and do that and see where it meets. All right, if you go ahead and find it, you're going to find that it is was 4 when H is equal to 6.76. So you're going to find that D is going to be equal to 6.76 times 3.6. Okay, and you're going to have to divide it back under to get 3.6. Okay. So you're going to get, so it's going to be, basically it's going to be 6.76 miles above sea level. Okay. So just 14.7 for those of you who have taken chemistry, this should ring a bell, right? You talk about moles, right? Your moles is 6.02 times 10 to the 23rd, 6.22 times 10 to the 23rd molecules at STP, right? Standard temperature and pressure. Standard pressure as pressure at sea level, 14.7 psi. Standard temperature is 25 degrees Celsius, right? So you guys learned this in chemistry, okay? Just kind of going back and kind of bringing up the memory there. Okay, and the next part is using regression, and we will do that in the second half. So we are done with the first half.